So in this video we're going to see how actually we've already encountered simple harmonic motion before, just we didn't call it that and we didn't realise it was lurking in the background. But we're going to see basically the connection to circular motion. So can we work out the solution to the simple harmonic oscillator using something we've already seen? And it turns out yes, we just need to think of uniform circular motion. So what's the horizontal displacement? That's to say the x component. So we've got here the x component and the y component on this axis. So this is just going to be some, this is just a physical disk. We're doing some circular motion around this, and we're moving like this in this direction at some constant speed v, and well, that's not too important right now. But the main thing is this is our y component, this is x component, so this is some two-dimensional circle we're doing. And what's the horizontal displacement of the particle as it goes around the circle? Well, we see we've got this radius r, and so we can see that we can just use trigonometry to see that this x distance, which is our horizontal component, is just given by r cosine theta, so r cos theta. So x equals r cos theta is the x component of the particle as it goes around. So we can imagine maybe we had this particle going around here, and what we do is we just get it. Maybe we put like a little torch in it or something, or a little laser beam, and we just get it to basically shine a beam down here. And so when it's there, it's shining a beam, lighting up that point. When it's here, it's lighting up this point. When it's here, it's lighting up this point. It's basically what we call projecting its position on just the horizontal dimension. So we're just having this 2D motion resolved down into one dimension. So when we're here, it's shining up to here. When it's here, it's shining up to here. So it already looks like we're kind of doing some oscillation back and forth when we think about projecting its point. So the horizontal displacement, the x component as it goes around the circle, is x equals r cos theta, where theta is whatever angle we've moved through. Then what is acceleration? Well, we know that the acceleration towards the circle is going to be given by, towards the centre of the circle, sorry, is going to be given by a equals v squared over r. And the thing to note here, and we're going to use this, we're going to say omega squared r, where this is r is our angular speed here. So we're going around with a angular speed of omega, and we're familiar with that from our previous videos on circular motion. But then we just want remember that's just the full component of a. That's our acceleration towards the centre of the circle a. But we want the x component of that. And so we're going to see that, well, if our a is like this, theta is like that, which means that theta is going to be up here. So our x component, remember, is going to be pointing inwards. So we're going to need a minus sign because we're going towards the centre of the circle. And we're going to call that ax for the x component. And that's going to be, well, whatever our a is, times by cosine of...
Hey guys, to continue watching this video and unlock hundreds of other super concise and exam board specific A-level physics videos, just click the Snap Revise smiley face. Join me today, and together let's make A-level physics a walk in the park.